Today we're going to start talking about energy. Once again, we seem to be lacking a little bit today. Everybody dragging a little bit. Got that long weekend. Trying to get ourselves moving, but like I said, be happy we're here in school and we're actually moving, not sitting at home. Trying to motivate ourselves at home to be able to get through class today. So be happy you're here. We're going to start talking about energies. First type of energy is kinetic energy. Kinetic energy is energy which a body possesses due to or possesses by virtue of being in motion. It is the energy of motion. Once again, we tend to be lacking it a little bit today. That motion, we all be going a little bit slower than we normally go. When we're talking about kinetic energy, anything that is moving, any object that is moving has kinetic energy. Me walking across the floor, me throwing an object, they all have kinetic energy. This pen, I throw it up in the air. Oh, it has kinetic energy. Has kinetic energy. Has kinetic energy. It is moving. Any object that is moving will have kinetic energy. How we calculate kinetic energy? Kinetic energy is calculated by 1/2 times its mass times velocity squared, 1/2 mv squared. This is your kinetic energy. I got my safety goggles on so you can throw. So mass, if a mass of 10, if a 10 kilogram mass is moving at a constant velocity of 5 meters per second, what's the kinetic energy of the mass? What's the kinetic energy of the mass? And once again, as you are already starting to do, you're adding this to your formula sheet. So we have 1/2 times 10 times 5 squared. So if we multiply these out, we should come down to what, Harley? 125. Let's see, let's take a look at the units. We have meter squared times kilogram per second squared. Let's take a look at these units here. And let's do some rearranging. We have a kilogram meter per second squared multiplied by a meter. Well, the question is, what is a kilogram meter per second squared? What is a kilogram meter per second squared? What unit is that? Well, let's break this down even further. We have a kilogram times a meter per second squared times a meter. A kilogram is a mass. Meter per second squared is acceleration. Well, what is mass times acceleration? That's equal to what? What would that calculate when it took mass times acceleration? What's Sir Fig of Isaac Newton say that is? Anna? It's a force. And what's force measured in? Newtons. So this here is a Newton times a meter. Oh, if I take a Newton times a meter, what do we come up with, Dylan? What is a Newton meter? A joule. That is correct. That is a joule. Come on, man. There's a reason why I asked you that question. It is a joule. So when you talk about energy, kinetic energy, we are still coming back to joules. $125 joules. With that, we just did a section on work that was also in joules. So the mind should think there's a connection between kinetic energy somehow and work, because both the units come down to joules or joules, doesn't matter. A change in kinetic energy is your final kinetic energy minus your initial kinetic energy. Your final kinetic energy minus your initial kinetic energy. This is your change in kinetic energy. A 50 Newton force is exerting on a 10 kilogram mass for 5 seconds. The initial velocity of the mass is 2 meters per second. How much work is done by the force? May the force be with you. How much work is done? Oh, let's see here. Let's assume frictionless. We'll assume frictionless for right now, just to keep it simple. Well, how do we calculate work? Work is calculated by force times distance, or displacement. So we know we have a force of 50 newtons, but we don't know displacement. But we do know that we have an initial velocity is equal to 2 meters per second, and we have a time of 5 seconds. We have a force of 50 newtons. We have a mass of 10 kilograms. Well, we have a force of 50 newtons. We have no friction. We We have a mass of 10 kilograms. What other value can we calculate here? Ozzy? Acceleration has to be what? 5 meters per second squared. Because we have force is equal to mass times acceleration. So we have 50 is equal to 10 times acceleration. So we have acceleration is equal to 5 meters per second squared. We still know we have the force here of 50 newtons. We have acceleration, we have initial, we have time. What is the displacement for this object? We have the initial t plus 1/2 at squared. What is our displacement, Jordan? 73, 72.5. So we have displacement of 72.5 meters. So we can find our work by taking our force, which is 50 newtons, multiplying by 72.5 meters. Brandon, what do you give for work? Joules. All right. Let's find the change in kinetic energy. Our change in kinetic energy. So let's find our initial kinetic energy, which is 1/2 mv initial squared. So we have 1/2 times 15, or our mass, which is 10 kilograms, times our initial velocity squared, so that is 2 squared. So we should get 20 joules. To find our final kinetic energy, we need 1/2 mv final squared, but we don't know the final velocity. So we're going to have to do some calculations. V final is equal to V initial plus AT. Go ahead and calculate your final velocity. And then calculate your final kinetic energy. We get 27 meters per second, final velocity. So we have 1/2 times 10 times 27 squared. Lucas, what's your final kinetic energy? 1/2 times 5 times 27 squared. Bennett, what did you come up with?
3,645.
3,645 joules. So if we find our change in kinetic energy, we have kinetic energy final minus kinetic energy initial. So we have 3645 minus 20. Nate, what's our change in kinetic energy? 3,625 joules. Now, if we take a look at our change in kinetic energy and what we did at the very beginning, we can see that the work that is being done is also your change in kinetic energy. If a constant force is exerted on the object will accelerate. Looking at, I'm not going to go down to here yet. If we take a look at what we're working on here, your change in kinetic energy is going to equal your work. What I'm going to do is I'm going to stop there, just because what we have to go through now is going to take a little bit longer than what we have left. It's formulation of what we're dealing with here, and arriving at the change in kinetic energy is equal to work. So we'll get to that tomorrow. We'll just stop it there today. Questions? All right, you have the last 5 minutes.